Have you ever looked at a high-end CNC machining service and kind of scratched your head at the numbers? Specifically, the tolerances they promise. Well, it turns out there's this fascinating story behind those numbers. One that opens up a whole hidden world, where a tiny fraction of a millimeter can be the difference between a perfect part and a super costly mistake. So let's break down the real cost of precision.
So this whole thing really kicked off with this brilliant question that popped up online. Why on earth would a professional service, with machines that cost tens of thousands of dollars, only guarantee a tolerance that seems, well, worse than what a cheap hobbyist 3D printer can nail on a single go? It feels completely backward, right? Well, the answer reveals a fundamental truth about what manufacturing is all about.
And here it is. This is the whole key. It's the difference between a promise and, well, a possibility. That 0.05 millimeters from a 3D printer, that's its capability. It's the absolute best it might do on a good day with the wind blowing in the right direction. But that plus or minus 0.1 millimeter from the CNC service, that is its promised accuracy. That's a rock-solid guarantee that every single part, whether it's the first one off the line or the 500th, is going to fall within that range. It's about consistency, not just a one-hit wonder. Now, to make these kinds of guarantees, the entire industry has to be speaking the exact same language. And that language is built on a foundation of standards that define precisely what close enough actually means in the real world.
At the very heart of this language is this concept of engineering tolerance. And it's not about being perfect, not at all. It's about defining an acceptable range of imperfection. It's the total allowable wiggle room from a target size, giving manufacturers a really clear window to aim for.
So how does this actually play out? Well, a lot of services use a standard like ISO 27068. Just take a look at the medium class on this chart. If you have a part that's supposed to be 30 millimeters long, it's considered perfectly in spec, even if it's off by plus or minus 0.2 millimeters. And that's not a mistake. It's a globally understood agreement that for most general parts, this level of precision is totally fine for it to function.
Okay, so if a standard defines the target we're aiming for, how do we know if a machine can actually hit it time and time again? That's where we get into these really cool concepts of precision and repeatability, which are measured with some very specific metrics.
First up is CP, or process capability. The easiest way to think of this is as a measure of precision. It asks, how tight is the grouping of the machine's results? So a high CP value means the machine is consistently spitting out parts that are very, very close to each other in size. It has a nice, small, predictable spread.
But here's the catch. Being precise isn't enough. You also have to be accurate. And that's where CPK comes in. It doesn't just look at the spread. It measures how well that tight little grouping is centered on the actual target dimension. You can be incredibly precise but also consistently wrong. CPK is what tells you if you're consistently right.
And this visual just nails the difference. Over on the left, you've got high CP but low CPK. The machine is making really consistent parts, for sure, but they're all off target. It's kind of like a great archer whose sight is just misaligned. On the right, that's the goal, high CP and high CPK. Consistently precise and consistently accurate. That's the sweet spot.
So what's the magic number? Well, for most normal manufacturing processes, the industry gold standard for a capable, reliable machine is a CPK of 1.67 or higher. This number is really a promise. It's a statistical guarantee that the process is under control and it's delivering exactly what the customer asked for.
Okay, now we get to the real aha moment of all this. Because achieving that high CPK, especially when you're working inside a very, very tight tolerance window, has a dramatic and, frankly, often surprising impact on the cost.
Here is the number that just stops engineers in their tracks. Chasing that mythical perfect tolerance of 1/10,000th of an inch, that's about 2.5 microns, can cost an astonishing 24 times more than standard rough machining. Perfection, my friends, is expensive.
And this chart shows you exactly why. The relationship between tolerance and cost isn't a straight line, it's exponential. As you can see, just going from a rough tolerance to a standard one doubles the cost. Then, trying to tighten that up to 1/1000th of an inch, bam, it doubles the cost again. Every little step you take towards perfection demands more precise machines, more inspection, more time, all of which sends the price tag shooting up.
So, if chasing these super tight numbers is so expensive, how do we make sure our parts actually fit and function the way they're supposed to, without breaking the bank? Well, the answer lies in a much smarter way of thinking about tolerances, one that focuses on how the part works, not just on arbitrary plus or minus numbers.
So here's the classic problem. Let's say you need to specify the location of a hole. If you use simple plus or minus tolerances on the x and y coordinates, what you're actually defining is a square area where the center of the hole is allowed to be. But the hole is round. You're literally trying to fit a round peg's function into a square hole's definition, and it forces you to use way tighter tolerances than you actually need.
The solution is GD&T, or geometric dimensioning and tolerancing. Think of it as a symbolic language that goes way beyond simple length and width. It lets designers specify what's truly critical about a part. Things like its flatness, how perpendicular it is to another surface, or its position relative to other features.
So let's go back to our whole problem. Instead of that inefficient square zone, GD&T uses a control called true position. And as you can see, it defines a circular tolerance zone. This perfectly matches the function of a round hole, making sure it will assemble with its mating pin every single time.
The result of this one little switch is just staggering. By defining a circular tolerance zone that actually reflects how the part needs to function, you give the manufacturer a massive 57% more tolerance area to work with. The part instantly becomes cheaper to make and easier to inspect, all while functioning exactly as you intended. It's just a smarter way to define precision.
And that really brings us to the final critical question you should be asking about any design. Are you specifying tolerances based on what the part actually needs to do? Or are you just calling out super tight numbers that add a ton of complexity and cost for really no benefit? Understanding that difference, that's the key to truly efficient and effective manufacturing.